works? Yes?
Yep.
Okay. Okay, so we kind of left off last time by just saying that deep learning is really about building these function approximations with small building blocks. And so I'm going to cover in a little more detail what those building blocks tend to be. I'm then going to quickly go over what I think are important steps in sort of using or building neural networks. But that will be closely tied to this interactive tutorial that I wrote on that will walk you through a couple of problems that we can solve with deep learning. And importantly, you'll sort of get exposure to all of these aspects, all of the things to think about, but also how the different building blocks work and how TensorFlow works and that sort of thing. Okay, so just picking up close to where we left off, sort of one way to think about machine learning and deep learning in general is that we want to build these sort of large function approximators. And sometimes they kind of just solve your whole problem. So you have some image and you want some output, a diagnosis, segmentation, something like that. And you want to build this function that approximates that relationship. So we talked about how in deep learning, the way we do this is we have these very, very small, very simplistic building blocks. And the idea was that if we stack them in all kinds of ways, we would eventually build really powerful functions, meaning functions that could sort of adapt to whatever the problem is. And then I demoed this sort of website where you can choose different problems and add neurons or these building blocks, and it kind of show how see how everything works. And I think this was shared on the chat afterwards, so hopefully people got to play with this. Well, I know some of you did because you asked me questions. And so today I'm going to talk about these building blocks. So the first one goes by many names, neuron and node, perceptron. But the main idea is that we have some input and we're just going to treat it as scalar for now. And then we do some simple operation on it and we get some other scalar out. And it usually looks something like this. We basically have two very simple operations, or maybe three, depending on how you count. We have the input is multiplied by some weight, which we tune during the fitting process or the learning process. It is then passed. So sorry, let me just. This is the input. This is the output. This weight is tuned or learned during the process, as we'll cover a little bit later. But your input is just multiplied by this weight. It is then passed through a function that we call a nonlinearity. The whole point of this function is just to make sure that y and x are not in a very simple linear relationship, but it's just slightly more complicated than that. This nonlinearity, I'm going to show examples, but this nonlinearity tends to be something very simple as well. And then we tend to add a bias term sometimes. And so it's a very simple relationship, right? It's all kind of scalar multiplication and addition with this sort of non-linearity that gets applied. Now, here's a couple of examples. These are the most popular non-linearities that we have. So one of them is a sigmoid, which basically it's sort of this formula up here, but the bottom line is that you're given any input between negative infinity to infinity, this nonlinearity will make this new input be will make the output be between 0 and 1, and it looks something like this. So that's one nonlinearity. Here's another nonlinearity, which is basically two linear blocks. So very, very, very simple nonlinear function, right? It's just sort of almost a linear function, but not quite. And that's it. That's really all there is to this. So this is, like I said, a very, very simple unit. But there are these two parameters, right, that get learned, the weight and the bias. And of course, as I showed in sort of the diagrams earlier, you don't actually have just one input, usually, to a perceptron. You have several inputs. And so we just modified that function a little bit by adding a sum in here, right? So for every input that you have its own little weight that gets learned, that gets multiplied with the input, and then you add it up before you pass it to the nonlinearity. So again, very simple. If I have 10 inputs to my perceptron, I just have 11 weights, right? The 10 weights from the inputs plus 1 bias. So 11 weights. But of course, as I stack a bunch of these, I start getting more and more weights into my network. And so by sort of the end, every layer, and here when I say a layer, I mean sort of one of these groups, every layer has this many numbers of parameters. It's basically the number of nodes coming in, the number of nodes that are being evaluated, and then the bias terms. Okay. Now, if the inputs and outputs are really large, like images, and you decide to use perceptrons in your neural network, these numbers tend to be very, very, very large, right? So, millions times millions of parameters. And so we end up not really using these types of nodes with images. But the bottom line is that this is probably the most popular type of unit that gets used in a neural network. And you can sort of intuitively see how perhaps from very small units that you just do small additions and then small nonlinearities, if you build millions of these units, you eventually have the power to do something interesting with that function. And that's it. That's really kind of the simple building blocks of neural networks. I'm going to take a second here before I go into convolutions. Do people have any questions? Like, was the math clear and everything? Water. Super clear, or people are still really afraid to ask questions? Okay.
Oh, I have a question.
Yeah.
So I was curious that how you know whether which activation function you should use, like ReLU versus sigmoid. Like, how do you know which will be more helpful in, I guess, like cleaning your data or working with your data to get a better result?
Yeah, it's a great question. And unfortunately, the only answer I have personally is that for the most part, for all the internal nodes, meaning not the first or not the last, I don't have a very good sort of technical answer. I have an empirical answer, which is that over time, as a field, we have learned what tends to work better. And the answer almost always is ReLU, which is this nonlinearity here. So the good answer, the good part of that answer is that, it's kind of solved. The bad part of that answer is that we're not quite sure why that's necessarily better than most other nonlinearities in practice. The final nodes usually have some important meaning. So you have to be careful what the nonlinearity should be so that it matches the type of output you have. So for example, ReLU does not output, actually neither of these nonlinearities have any negative output, right? They're both, so the sigmoids are between 0 and 1, ReLUs are between 0 and 10, or 0 and infinity. So if you're looking for an output that has negative values, you wouldn't want to use one of these. But that's the only time and the only reasoning I can think of that you really need to kind of sort of sit down and think about it. Does that answer your question?
Yeah, thank you very much.
Any other questions? just going to assume that means that they were clear. Okay, so by far the most important building blocks for images are convolutions. And so it's actually very, very similar story, but now we think of the input data as images and the output data as images. And so we have the same, roughly the same equation, but this time instead of multiplying a weight with our image, we're going to convolve a very, very small kernel with our image. And so it's the same sort of story. The input is X, except here it's a 2D image, or it could be 3D or 4D, but basically it's not a scalar. The output is also a 2D image, which we sometimes call a feature. You have the same idea in terms of what is learnable, what's going to end up creating your function. These weights, W, and the bias term. Except here, the weights is not a scalar. It's a very small kernel. Well, usually very small. It could be as big as you want, but usually it's a very small kernel. And by kernel here, I just mean another very small 2D matrix, maybe a 3x3 or something really small. Okay. And this operation here, oh, sorry, you still have your nonlinearities. That is exactly the same as before, the same way it works. But the important difference here is that it's a convolution, not a multiplication. And so if you haven't seen convolutions before, I'm going to give a very, very short introduction. And I think it's just an intuitive introduction on how it works. I'm going to do away with equations. And so let's assume the matrix on the left is our image. Okay, it's a small image. It's 5 by 5. But let's say that's our image. The matrix on the right is our little kernel, W. Okay. And now here's how this whole thing works. So I have the input on the left, and the result is on the right in green. And so the input is that 5 by 5, but now what I'm doing is in the top left corner, I'm multiplying the kernel. And I'm doing it element-wise. So this 3, which is from the image, gets multiplied with 0, which was from the kernel, right? So if I go back, there was a 3 here and a 0 here, right? So the 3 gets multiplied with a 0, and then it gets added to 3 times 1, then it gets added to 2 times 2. And so you do all this matrix, element-wise multiplication, and then you add the 9 entries. And that gives us 12. Okay? And then once I'm done that, I go to the next step and I do the element-wise multiplication. I do the addition. It gives us 12 again. And then in this corner, it gives us 17. And then the convolution basically goes over the entire image and sort of computes this. So let me give some examples of what that actually sort of means in practice. And so I wrote a very, very brief tutorial on this at the address below. So you can sort of go type it in and actually play with these kernels and so on. But here's how it looks like on MRIs of the brain. So here's the input to a convolution. Here's a kernel that I'm selecting. So this is what we call a gradient kernel. It'll basically sort of highlight edges in the image and the sort of direction of the intensity gradient. And so if I convolve this image with this kernel, I will get this result. Okay. And so, for example, here around the ventricles, we see that these are highlighted in this, what we call feature vector, or the output of the convolution. Does this illustration make sense for a convolution? Or does anyone, does anyone have questions on any one of these 3 things on the screen? No? Okay. Here's another example. This is a Gaussian blur. So this kernel is a little bit bigger, and it basically emphasizes the sort of data itself that's at the center of the convolution when it moves around, but it incorporates some of the pixels around. And so what this kernel is doing is it's going through the image and it's blurring the image a little bit, mostly emphasizing sort of a copy of the data, but mixed in with the neighbors of every voxel. And so you get this slightly blurrier image. So again, if you go to this address here, there's a bunch more examples of kernels, and then you can also play with the kernels yourself and see what the effects are of different kernels. Okay. And so that's really it for the second most popular element in neural networks. So again, it looks very similar to the first one, but we're doing a convolution. There's slightly more weights. Now, again, most of the time, we don't have a single image going into one of these operations, but it's really a stack of images, or what we tend to call features, that are going into one of these operations. So again, we're going to do the sum, right? We're going to do a bunch of different convolutions for each input image or each input channel or each input feature. We're going to come up with a separate kernel that we're going to learn over time. That's going to get convolved with our image. And then we're going to sum at every voxel, we're going to sum that data, pass it through the nonlinearity, add a bias, and that's our output. So it's a little bit like you convolve a stack of images, add them all up, and that's our result. Okay, so we're back at this figure now, but these operations are slightly different. And so we tend to use these operations when the input is something like an image or a volume. These convolutions have several advantages that I'm going to talk about in a second, but the number of parameters is very similar to the number of parameters in normal perceptrons. It's the number of features coming in, although these numbers of features tend to be much smaller than with perceptrons. We might have something like 32 features or 16 features. The number of features going out, so the number of features coming into a layer, the number of features going out of a layer. There's a little multiplier here, which is the size of the kernel. So that tends to be something like 3 by 3 or 5 by 5. And then the bias terms. So this is the number of parameters that will be in a single layer of your network. And so if you have a lot of features coming in and out of every layer, and then you have a lot of layers, this number can also get very large, often in the millions. Now, some quick observations about these last few slides. So as you've seen, even in as I was talking, I kind of mentioned several terms that all kind of tend to mean the same thing. And so this is because deep learning is this incredibly fast evolving field, and it's kind of there's core machine learning being done, but also it's super applied. And so everyone kind of uses their own terminology. What you will often see as referred to one of these circles that I've had is sometimes they'll be called perceptrons or neurons or a node or a feature or a latent variable or a hidden variable or a hidden node or a hidden neuron. So all of these mean the same thing, and they're basically referring to that operation that's sort of a multiplication or a convolution followed by nonlinearity followed by a bias. There are sort of convolutions or features or channels. These tend to be sort of the output of the convolution operation. This is what people usually use to mean that, right? So that Y variable that I had in my slides, people will refer to it as features or channels or things like that. And then you'll see other terminologies and that kind of get mixed up, like fully connected versus dense. These are layers that use a lot of perceptrons, and people use different names to kind of mean the same thing. And when handling images, which is what we tend to do the most with neuroimages, MRI, CT, stuff like that, we tend to use convolutions the most. Fully connected layers or dense layers that use neurons tend to have several disadvantages. You would probably use a neuron per voxel and then try to connect them all, and that would be enormous. It would be millions by millions of connections. So that would be too large of a neural net. It wouldn't take advantage of the spatial structure. It would just treat each voxel independently. So we tend not to use fully connected layers for the most part. Convolutions, though, are much better because you're working with these small spatial kernels, these 3x3 or 5x5 or whatever kernels. Those kernels have the ability to take advantage of the spatial structure of the image. You apply, because it's a convolution, you tend to apply this kernel to the entire image. So it's one kernel per image or per image feature rather than per voxel. So you have substantially fewer parameters in this operation. And so at the end of the day, the number of parameters really depends on the number of input features and output features you have, not the size of the image, which is a really cool sort of property. Okay, any questions on this kind of quick whirlwind on the building blocks of neural nets? I'm gonna take a second. No, no questions. Nobody wants to unmute. All right, so we kind of had this, I kind of had this sort of planned out to do half the lecture on these slides and then half the lecture on the tutorial. So this next slide, I thought of sort of what are the important sort of steps in the pipeline when you approach a new problem where you want to use deep learning. So this isn't about sort of developing a new deep learning algorithm, but more you want to use neural network to solve something. And I thought, what are sort of the big things that you think about? And so I have them on the slide coming up, but then I also took them and built them in the tutorial. And so they're kind of like headings in the tutorial, some of them more important, some of them less important. And so once I give the slide, I'd like us to sort of go to the tutorial, and I'm going to want everyone to kind of load it up on their own screen so that you can sort of click through that tutorial. All right, so the tutorials are there. It's a very unfancy website. So the first thing is to think of the task. I think this comes with experience, but a lot of the times you have some problem where you think that deep learning might help, but deep learning will not necessarily solve your entire task, or maybe it's not the most appropriate thing to do. And maybe some part of it where there's some function that needs to be approximated is the best place where deep learning can be inserted. And so this is something that we'll cover in sort of later lectures in more detail, but I do want to emphasize that a lot of times it's best to not just kind of assume that deep learning will solve your entire problem from start to end, but more about think about what parts of the problem sort of machine learning can help with. Data is very, very important. And so in the tutorial, you'll see that I have all these explanations about how to best treat data. So first, we have to very carefully think about the properties of our data. What are the shapes? What's the distribution of our data? What are the intensities? What's the variability? And those sort of things. To a large degree, those properties will determine how well deep learning is going to work. And so it's very good most of the time to spend some time at the beginning of your project to really investigate your data, compute statistics, visualize, 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 visualize all the time. And these things will, in my experience, very often determine both the type of deep learning you're going to use, but also how sort of an estimate of how effective deep learning is going to be. And then I want to emphasize that you should never take your entire data set and train a neural net. You really, really want to split your data up as much as possible and keep a bunch of your data completely unseen. I described this in more sort of more details in the tutorial, but basically the more data you see, the more you are kind of tainting the entire process, and you don't know if you've built a network that solves your problem or you've built a network that only solves your problem for your very particular data that you had at the time. And so what I usually recommend is that you separate the data into a training set, which can be substantial, a validation set, and then a completely held out test set that you almost never look at. And that's because the more we look at our data, even visually, the more we will influence our sort of design process, and therefore we are essentially overfitting to the data that we've seen, right? And again, I go into this in the tutorial a bit more. Okay, so it's a huge chunk of this is on data, and that's not even sort of going into the extensive pre-processing you might have to do, or gathering the data, normalizing data, that sort of thing. We're gonna look at that later, but I want to emphasize that even if the data has gone through all the pre-processing and stuff, really, really, really understanding your data will save you tons of time later on. And then it's probably time to start thinking about a model and an architecture. I tend to separate these. I think of the model as the relationships between the entities in your problem. So maybe the MRI and the diagnosis, or the MRI and the segments, anatomy, the segmentation, things like that. And so if you understand the relationships between these things, maybe write them down one way or another. I think of all that as being part of the model. And then separate from the model, you have to design, think about the best neural network architecture that will try to help you solve your task. Right? Again, we're going to cover more in future sessions, and there's more in the tutorial, but just as a big picture, the model deals with the entities and relationships, and the architecture is specific to the neural network. Most of the time, these are also terms that will be intermingled. People will say model to refer to the neural net. They'll say architecture to refer to some other sort of aspect of the neural net. And so we have to just deal with this kind of flexible terminology. Once you've sort of decided on that, you will want to fit your architecture to the training data. Again, there's a terminology issue here. You'll see, you will hear training, learning, fitting. All of these basically mean you will tell the network, here's the data, here's the network, please adapt the parameters to fit the data. This is a huge part of neural networks. It's non-trivial to do sort of learning properly, but at the same time, we have quite a few very successful tools in various libraries right now that can make this work. And then once you fit the data, how you actually evaluate your results is really important. I will emphasize both statistical analysis that you should do always, without exception, and visualization, because in our world, everything we work with tends to be very visual. And so I have some examples. Yeah.
Sorry, there's a question for you. I don't know whether you see the chat box.
I don't see the chat. Yeah, so someone, yeah, thanks.
Oh.
So
Yeah,
when
sorry.
you talk about training data, is that additional data to acquire and not using the final analysis, or a small randomized portion of your data set, or neither?
Yeah, good question. So it depends on the task. Most of the time, if you have a data set, either your own data set that you've acquired or data you got from somewhere else, if it's big enough, you will split some portion of that specifically for training your network. And once you do that, I certainly would not use this training data to do downstream analysis. Or at least most often. It depends on the task, but most often I would not use that training data. So if you have very limited data, you only have 10 subjects, then it gets a little bit tricky. And then you might want to train on 5 and keep the other 5 for analysis and so on. Does that kind of answer it?
Yes, thank you. And thank you, Lila and Allison.
Great. Okay. And
Quick
so
question.
then yeah.
Can I, quick question, sorry. Would you, just to see how a good is doing on a sample split, like use, like for example, I have hundreds of neurons in one slice, split the slice into like 2 different portions and look at like how using half of it of the slice for like training and the other half to just validate or to look at how it did or not? Or would you just complete the slice and using on a completely different slice for validation?
So, so first of all, just to be clear, by neuron here, you mean actual neurons.
Yeah, sorry.
It's okay.
Wait, did I said sorry?
Right. So I would say that the answer, I think the answer to these sort of questions is usually that you kind of get what you pay for. So if you're doing it on the same slice, but you are, let's say cutting it in half and training and validating, then when you look at the validation and you get a certain result, the best you can say about that result is, okay, this is how the neural network does in these data, right? And so for you, it would mean in this slice. Now, is it gonna validate as well in a different slice? You don't know that yet. Most of the time, the answer is yes, only if the second slice is very, very similar to the first in terms of kind of how it looks like, right? If you have enough data, I would almost always advise that you validate on a completely separate slice.
Okay.
Yeah, because that gives you a better idea of this notion of how well it generalizes to other slices, right?
Okay.
Okay. The unfortunate truth is that at the end of all of this, you have to go back and repeat steps 3 to 5 a lot of times. Now we do have some sort of insights that we've built in the lab, a few that a lot of us have that we kind of know, what are the good architectures, what are the good training strategies, how to best look at your results. But unfortunately, a lot of times there is some tinkering. And so going back and repeating these steps. And because of that, you really, really, really don't want to look at your test set until the end, right? So that you can keep tinkering with your data and sort of know that you have some data that you've never looked at. Okay, so that's kind of the outline of how the tutorial is built. Well, we had this kind of debate in the minutes leading up to the session about how we would do the tutorial. So I think what I'm going to do is I'm going to bring up the tutorial myself as well, but I really would love for everybody to kind of load it up. So if you just go to this address, people can see my Chrome window now, right? I hope.
Yeah, it's just really small.
Just really small. So, oops, sorry about that. So
I mean, that's the address is. Yeah.
yeah,
but
so the address is maybe, is this kind of better?
Can you paste it in the chat?
I can certainly try.
We'll see your teams, but just as a warning. I can paste it in the chat, I'm sure. Let me work on that and you can continue.
All right. So, you know, me going through the tutorial in front of everyone is probably the least effective way to do this. So I look for everyone to go to it. And so as a kind of a meta comment, this tutorial is written in a framework called Google Colab. It's basically a mix between taking notes in a notebook and running Python in that notebook. And so the really awesome thing is you don't have to install anything, download anything. You just kind of go to this address. You go to this address that I pasted or somewhere, and go to tutorial 1. So there's a tutorial on convolutions, but it's just kind of to play with. But tutorial 1, and then you'll get this, and you can immediately start running Python inside it, which is awesome. And so we're going to do all of the tutorials this way. And you know, the great thing about it is you don't have to worry about all this stuff about, you know, setting up Python and so on. And so I am going to have to leave at 3, so I don't know how to kind of go about this. I do want to let everyone know, you know, this is available after the session, and you can play with it. You can ask questions on the channel afterwards. But as an example, I really would love for everyone to not just kind of click on everything, but you know, read what I had to say. I think it sort of provides insight for every block of text. This very first block here is just set up. So this cell, you know, which is the only thing here that looks like code. If I press play, it will. Oh no, I have to log in. Okay, I'm gonna log in. All right, so everyone log into your Google. Okay, and so we're back here. So to just run this, I just have to click play, this little play button, or there's a shortcut. I think Control Enter will also run it. The very first thing that is run will take a little bit because it sort of has to load Python and everything. This very first entry will basically install Neurite, which is the library that for the deep learning library that we support here. That we've all been kind of contributing to. This just does a bunch of imports that Andrew kind of taught us all about in the last session. It basically brings in a bunch of libraries into our workspace so that we can go through it. And then there are 2 sort of tasks that I've set up. One of them is classification on a data set called MNIST. It's very simple, has nothing to do with neuroimaging, but it sort of allows us to think of all the steps, you know, the task, the data set, the model, the architecture, all that sort of stuff. And then after we do this, the second part is segmentation on actual brain MRI. So we load in a bunch of brain data, and then we go through the same steps, but for brain data. Given that there's only 10 minutes left, or no, well, 15 minutes left, I'm not sure how to proceed. Allison, Leah, do you have an idea what might be best, or do other people have suggestions of what they how they think this would be best beneficial, or should people could also go and do it by themselves and ask me questions in the next 15 minutes or so?
Well, what we learned is that right now Iman's the only one that can control the breakout rooms because he's the organizer of the meeting, and I feel bad making Iman do it. So I think why don't we just work on it in this big meeting, and if people want to leave and work on it on their own, they can. I
mean, we can try to see if other people have also control over it, but I've never done it.
You want to go for the madness?
I mean, so just as a comment, just before we decide on this stuff, I'm very happy to just take people's questions off, like away from this, like after this session as well. But I do have to go at 3. My son has a doctor's appointment, so I can't like sort of, be a little late. So we kind of only have 10 minutes, so that's why I'm kind of wondering.
Yeah, I think because we're short on time, we'll just stick to this room. And anyone who wants to stay on, work on it together, can do it here. And if you have questions, you can ask. And I might still create a separate working session in the education channel for anyone who wants to do more after 3 o'clock, just because we might end this session and end this recording and everything.
Yeah,
so
that
yeah,
sounds good.
Yeah, okay.
I can start going through it, and then for sure we're not going to get through all of it. But do people have questions about anything I covered or how Google Colab works before I get going? Because if we end this and then you can't get Colab started, that's a bigger problem. So
I have a general question. So it might be a bit off topic, but I noticed that you were using TensorFlow here. I've also heard of other packages such as PyTorch. So I was wondering, like specifically with PyTorch and TensorFlow, what are the merits of one over the other? And if I'm trying to like learn, which one should I start with?
It's a great question. It's a bit of a, so my personal answer, and I think everyone has a different answer. My personal answer is that TensorFlow and PyTorch have roughly the same capabilities now. They have a intermixed history. For a while, TensorFlow was very popular, and then PyTorch got started, and now it's kind of like the cool thing in the machine learning community. But like with everything else, everything comes and goes. So right now there's a different language called JAX, which seems to be getting most of the attention of the newcomers. And so my answer is, I think what matters is that both of these frameworks can have roughly the same features. And so I would argue it doesn't really matter what you start with. I think PyTorch is probably more popular by a little bit in the research community, and TensorFlow is probably more popular in kind of the tool building community, like as in the deployment and industry and that sort of thing right now. But these are very temporary statements. 2 years ago, it was different. 3 years ago, it was all MATLAB. I'm guessing next year it'll be more JAX. So in terms of what you use, that's kind of the mess we're in. Everything I have in this tutorial is very fundamental. So I imagine even the lines of code would be very, very similar between TensorFlow and PyTorch. I'm sure other people can jump in and argue strongly for one or the other, but that's my kind of balanced answer. Does that help? Or are you still not sure what to start with?
That helps. Thank you.
Sure. Any other questions?
I have a question getting back to splitting data into train, test, and validation sets. Is there like a gold standard you see in papers like 60-20-20, or is there some sort of ratio that would raise a lot of eyebrows of reviewers if you were to use it and might kill your paper?
I would love it if papers even did the split properly. They don't. They don't to such a degree that good machine learning conferences like NeurIPS make you sign off on the fact that you have split your data that way when you submit, and people still don't. I don't know of a ratio, but I would say that it depends dramatically on the amount of data you have. So if you have a ton of data, then putting most of your data in training makes sense, because then you can build large models with large training, and that's where deep learning tends to be more successful. So, MNIST has 60,000 images. You want to put 50,000 or 40,000 of them in training. The reason for that is because you have enough left over that you can have a very good test set so that you can make statistically correct statements when you make your conclusions at the end. If you work in our world where you have 50 images, if you're lucky, it gets a little more tricky. I'd say you want to leave at least 10 images if you're in that scenario for test. And so you probably want to leave 10 images test, 10 images for validation, and the rest for train, something like that. But it all kind of depends, right?
Okay, thanks.
Yeah. Unfortunately, like I said, a lot of my answers are, it depends. It depends on the task, and it kind of depends on like how variable your task is and all that sort of stuff. Let's see what to do with 7 minutes. So, okay, let me just cover briefly what this tutorial does. So I talk about the task. And so in MNIST, the task is you get images that look like this, and you want to say what the digit is, right? Like this is a 9, this is a 0, this is a 7. A lot of this seems easy for us, but it's not necessarily easy for computers unless you give them a lot of help or you build big machine learning models. And also sometimes it's not even easy for us. Some of these, a 7 looks like a 1 and vice versa. So I talk about the task. I show an example of how to bring in easy data that has been pre-processed and packaged for us. And then importantly, we want to visualize the data, right? And a lot of the times when we visualize the data, we see problems. One of the problems here is the data is not perfectly normalized to what we want. So I sort of cover how to deal with that. We then go into, and so here we split the data into validation, train, and test. I then go into model and architecture. So as you can see, there's a bit of a write-up here. Hopefully that helps people. There's different ways to think of the model, sort of how are the relationships between, the images and the labels or the classes, the digit, and how to think about that. And then I talk about architectures. Now, most of the time when you see images, you might want to use convolutional operations. But just to get us going, I first show an example with perceptrons or neurons. And I show an example of how to build a very simple architecture. Okay. In general, an abstract idea here is you first build the architecture and then you give it data. So when you build the architecture, it's somewhat abstract. It's an abstract entity. It's an entity that knows how much data is coming in, how much data is going out, and kind of all the details of how it looks like, but it doesn't see any data at the beginning. It's just an abstract entity. And so we have to build this abstract entity, which is called a graph in all of these frameworks, tensor graph. And so we I describe how to build the inputs, describe how to build the sort of internal representation. There's a little bit of description of how to think of the outputs. And then there's a diagram here of the model. The input, kind of 3 layers. This is a very small network as an example, in the output. I then go into the learning or training strategy, how to think of learning or training and what we tend to use nowadays. And then the code to achieve it. As you can see, the code is actually very, very, very small. Most of this code is sort of documentation that I wrote. So, it's actually just sort of 4 lines of code to get everything ready and train it. I talk about how to understand or how to look at the training process. So how do you track it? How do you track kind of how your network is behaving? on train data, on validation data, how to interpret this graph, of how sort of it behaves as time progresses. And then talking about how you could visualize your data and sort of what's helpful. Again, it's all kind of basic. It's sort of first line of evaluation, but I find it to be the most powerful. So those are kind of the steps and the takeaways. And then I do the exact same thing with brain MRI. So what's the task? I tackle a segmentation task into white matter, gray matter, CSF. What's the data? And so Andrew has prepared some data for a different project that we used here. And so we get the data, we have to read it in, we split it, and then we look at it, right? Again, visualization. So here's a bunch of brains. Here's what the segmentation maps look like. Again, how to think of the model and architecture. Very similar model, but now we're dealing with convolutions. And so I describe how to build these convolutions and what are the properties that matter. Again, training and learning. This time we learned a little more what the sort of training graph looks like, and then we visualize some results. So that's what the tutorial does. I try to cover it here in 5 minutes since we were ending, but please, everyone, go and run these and read the information that I have. If it's not clear, please let me know, ask questions, all of that. And so the next time we have a session, I'm going to assume that people have gone through this tutorial. And I think that's it. Any kind of closing comments? Questions? Did it all make sense? Were people able to load the website?
You got it. Thank you. I know I was able to load the website. Looks like a couple other people were. But I don't know if people were up for just getting right into it. But if you are, I created a meeting link in the education channel that you can join and start working on it together. But if you're going to do it later, feel free to form your own study group or do it independently, and let Adrian know how it's going.
Yeah,
or let all of us
absolutely.
know how it's going in the education channel. So I think we could all benefit from that.
Sure.
Okay, thank you, Adrian.
Okay, thank you.
Thank you.